Are we opening? Open. Here we are. Okay. Say again? What about it? Yeah. Yes. Yes. Huh? Newton, he had 3 laws. If you want to be important, you have to come up with laws. 3 of them is a good number to come up with. Okay? Right.
As long as you know?
Yeah, only 3. What a deadbeat, yeah. Okay. Newton's, so I should say, it's popular enough in the exam to ask you, what is Newton's first law, what is Newton's second law, what's Newton's third law. So, it's also important to remember which one is which. So here's the first law. So if a body is at rest, it remains at rest, or if it is in motion, it moves with uniform velocity until it is acted on by a resultant force. Oops, sorry. So in other words, to put it simply, if something is at rest, it will stay at rest. And if it's moving with a constant speed, it will stay moving at a constant speed. Unless the force acts on either of these situations. I'm recording this, am I? Yes, I am. Okay, do you have the first law? No. You have it? Oh. I still other people writing. Okay, so let me explain for the people who are ready. So what this law says, if something is at rest, it will stay at rest unless a force acts on it. Also it says, if it's moving at a constant speed, it will stay at this constant speed unless a force acts on it. This is his first law. So in other words, that ain't moving until someone pushes it. Okay? And if it's already moving, it will stay moving unless somebody stops it or, helps it. It won't start moving. It will stay at rest, and if it starts moving on its own, then you have broken the first law. Congratulations. Okay, second law. The second law we've actually already done. The second law, actually, just to be clear with the first one before I go on. So look, an object, you don't need to write this down. An object at rest will remain at rest unless acted on by a force. An object in motion will continue with this speed unless acted on by a force. This is his first law. Okay, now the second law. Force is the product of mass and acceleration. Now you can write down F equals ma. That's what we already did. Yeah, the second one can be stated as simple as x equals ma. There's another way to state it, which we'll look at in a different lesson, involving rates of change. But that gets its own lesson. Okay. Yeah, that's the one. So force is mass by velocity. Newton's third law, for every action, there is an equal and opposite reaction. Yep. So what the heck does that mean? So here's one example by what is meant by action-reaction. So if the air comes out of the back, then the balloon goes forward. So the air coming out the back is the action, and then the balloon going forward is the reaction. Here's another way I put it, Newton's third law. Here's my simple version of it, okay? Newton's third law, if you do stuff, stuff happens. Alright?
In the life.
What?
We always do this in the life.
Yeah, yeah.
Rejection of the action.
Do stuff, stuff happens. Basically. Here's another important example. So if we look, maybe something like this here. So, what force is this called? Weight. Yeah? So the weight force, what will the weight force do? It'll bring it down. But it stops here. And the reason it stops is because the table is given a force up, like in my picture. So this force up is called the reaction force. And this is the weight. And they are equal, but they are opposite. This is a plus, and this is a minus. The same when you press against the wall, okay? So my force is going in, but I don't move. Why not? Because the wall is pushing me with the same force. So this is the action, and then this is the reaction. Okay? Yeah, the biology teacher doesn't believe in this law. He thinks it doesn't exist. But I promise you, when you push against the wall pushes back. Okay? In Soviet Russia, wall pushes you. Okay. So just to be clear, the reaction force is the force provided by the reacting object. You don't need to write that down once you know what I mean. So here, the reaction force, is it going up or going down? Reaction force is going up. And here, where's the reaction force? To me or to the wall?
To you.
To me. Yep. Okay, good. Good. Right, so let's have a look at some examples here. So here's our first one. Please write it down. Okay, great. What is a new word in this sentence that you might want to learn? Here? There's a new word here which I've not used. Just Grace first. Yeah, true, that's a new word, yeah. And what about the second line? You see that word, exerted? Do you know what this word is? No, I didn't think so, because this is a new word. Amanda, do you know this word? No, or Sophie? No. So exerted is a verb, and it means basically push. Yeah. Now the reason I'm telling you this is, these are the types of verbs in the exam. So in the exam they won't say, push. They would say exert. Or, does anyone know another word that means like push? Press, but they wouldn't say act. So in physics we use words like exert, which means push, or act, A-C-T, also push. Okay, so you need to note these words for the exam. Exert, act, they both mean push. Let's have a look at this. This one's actually not so difficult. If I draw it, it looks like this. You have 20 kilograms here. Fahad, how big is this force? Not 20, no?
190.
Yeah, 196 newtons. Is it? How did you get that?
I find the mass.
Yeah, the mass is 20.
20 into 9.81.
20G. Isn't that the weight?
Yeah.
Yeah, which is, what did you say it was?
196.2.
Okay, we'll just go with 196 newtons. Now, this force is balanced, meaning the block is not moving. So Newton's first law and Newton's third law says that there must be a force here that is equal and opposite to cancel it so it's not moving. So basically 196 newtons is here. So just to be clear what I'm saying, Newton's third law says there's a reaction force. And Newton's first law says that this must be equal to this because it's not moving. So there must be no force. Okay, I'll do another example now. Can I scroll down? Go to the next example? Yeah? That's yes. Okay. Now you don't need to write all the English here. You can just draw the picture. It's the same, except it's 200 kilograms and there's a man trying to lift it. So let me draw it for you. It looks like this. This is 200 kilograms, and also there's a man here trying to lift it. That's a man. That's a man. Okay. Right. So, Amanda, what's this force going down? What's it called?
Weight.
The weight. And what's the formula for it? mg. So here it will be 200g, which is, where's the calculator? 200 times 9.81. 1962 newtons. Oh yeah, I should also say the question said that there was 1000 newtons given by the man. Also, the table, by Newton's third law, the table must be reacting as well. I'll call this or for reacting. But the or is not 1962 here. It's not. Newton's first law says that this force going up must equal this force going down because it is not moving, or not accelerating, I should really say. So that means or plus 1000 must equal 1962. So therefore or equals 962 newtons.
What if the same man has lifted it?
Well, the man can't lift it here because his force is less than the weight. Now, good question though. What if he did lift it? So for example, what if the man's force was 1962? Yeah, if his force was 1962, it would just about start to lift at a constant speed. What would the reaction force be, do you think? It'd be 0. Yeah. So if the man actually could lift with 1962, then the or would be 0 because the table is no longer pushing up because the man has fully lifted the block. So the or would be 0. What would happen if the man lets go? If the man lets go, what would the or be? It'd be 1962. In other words, the table is providing all of the support. Yeah, you need to go, yeah. Okay, next example. Can I go to the next example?
Yes.
Oh no, that was the last example. Oh no, sorry, that's another example. And there's another example. My goodness, how many examples do I have? I will do this one, but maybe not this one. I have too many. Okay, I'll do this one. Right, you don't need to write this down. I'll just draw the picture for you. So here we have a weighing scales, and here we have a book on the scales. You know what I mean by weighing scales? It tells you how big the weight is, the mass. What else do I say? It's half a kilogram. So this is 0.5 kilograms, and it's placed in a lift. It's like it's put into an elevator, or somebody just lifts it up. So somebody comes along and they move it up at, I think I said 1 meter per second squared. Okay. So my question is, before he lifts it, what does the weighing scale say? Well, the weighing scale says that the weight is equal to mg, which equals to 0.5 times 9.81, which equals 4.905 newtons. Just so you know, I won't follow my question exactly how I wrote it, okay? I'll do it a little bit differently. Alright, so my question now is, if I lift the weighing scales up, do you think this number will increase or decrease on the weighing scales? So imagine this is my weighing scale, and I put something on it. Maybe this will be better, yes. And then I start to lift it up.
The weighing scale or
the weighing scales with the mark on it.
Okay.
So I move it up. No, not the same. The mass will be the same, but I don't care about that. I care about what the weighing scale says. So if I lift this up, will the weighing scale increase or decrease? Now you know it changes because if you jump on a weighing scale, you see it moves. So will it increase or decrease? Increase. You're saying increase, yeah? You're saying increase, yeah. It will increase. So my question now is, how much will it increase by? So you might think, well, why is it increasing? Because is the mass different? No. And the reason it's increasing is because the reaction force changes. In fact, the way you should think about a weighing scale doesn't measure the weight. What it does is it measures the reaction force. When it's on the ground, the reaction force equals the weight. But when it's moving up, which is bigger, the reaction force or the weight? The reaction force, because it's going up. So that's why it will get bigger on the weighing scale. And likewise, if I drop it, what will happen to the weight here, the reading here? It will decrease, yeah. Okay, so let's calculate it now. So, if it's moving up, there are two forces here, an R and the W. And the W is always 4.905 newtons. But this R will be bigger than the W. Okay, so I have, by Newton's second law, F equals ma. Or minus W equals ma. Or I don't know. W I do know. M I do know. And A, what's the A? 1. It's going up with 1. So look, the ore is now 5.405 newtons. It was 4.905 newtons. That is 10% more. Now, does your weighing scale use newtons or kilograms? Kilograms, but it really should use newtons because it's measuring weight. But it uses kilograms. So at the beginning, what will it say the mass is at the beginning? What is the mass? 0.5. But when the weighing scales is moving, it won't say 0.5. What will it say? If it's 10% more, it will say 0.55. Yes.
Normally the weight is your weight.
Yes. No. It's called weighing scale, but it doesn't really tell you your weight. What it's really telling you is your reaction force on the weighing scale, which is usually equal to your weight. Only if you're not moving and standing still on the ground.
Understand?
Yeah.
Like if my weight is 84.
Yeah. No, that's your mass.
But the weight is 84.
I know, it's not supposed to be called a weighing scale. It's not telling you your weight, it's telling you your mass. The name is messed up. A weighing scale shouldn't be called a weighing scale because it doesn't tell you your weight, it tells you your mass. It should be called like a mass scale. If a weighing scale was really a weighing scale, the numbers would be in newtons. This is really what your weight is. Anyways, this example here, it's a little bit difficult, I know. But do you see how I got the 0.55? What did I do, Casey? What did I do? KJ, sorry. What did I do? Casey. It's going to stick now. KJ, what did I do?
5.405 divided by D.
I don't know, how did I get 0.55 from 0.5? 10% more, because the reaction is 10% more. And what else do I want to know? Yeah, okay. The last thing I'll ask here, so I list the weight scale is here, it says 0.5 kilograms, and I move it up, and it says 0.55. So my question is, if I let go and drop, let it fall, what would the weight scale say now? Anybody know?
Depends on the resolution of the force.
Yeah, so what I did was I lift it up, and then I let go, and just let it fall.
Minus 10%.
Nope.
Go back and look at that.
Nope.
Well, it depends on the acceleration.
Yeah, well you have the acceleration, 9.81.
Then it could be...
The answer is, it will be 0. Because if I drop these two together, if they're both falling together, this is not pushing up on this. They're both falling at the same speed. There's no longer any reaction force. This is not supporting the mass. So if I just let it go, it will say 0 here. There's no reaction force. They're both falling with the same acceleration. So what does that mean? For example, if you were on a weighing scale in an elevator, and if the elevator starts to fall because somebody puts the cable, the weighing scale would say 0, and you will feel yourself lift off the weighing scale as you both fall together. So there's some, I think there's some rides at some amusement parks where you go down really fast. And if you go down fast enough, you feel like you have no weight because you're no longer pressing against the ground. You know what I'm talking about? Because you start to feel there's no force anymore.
What do you call it?
This one?
No, the...
Free fall?
No, free fall. It's in the, it's in the park, you know.
I don't know. I've never been to one. You tell me if you find out. Okay. Okay, I'll just do Ferris wheel, I guess.
Ferris wheel.
I just want to go back to this example here as one more question. The only difference I'm going to make is instead of having 1,000 going straight up, it's now, I'll change it. Bye bye, Mr. Man. It's now going to be 1,000 newtons at an angle of 45 degrees.
Then I know.
So there's not too much of a difference, except this here will be 1,000 cos 45, and then this one here will be 1,000 sin 45. So if I look here, what number do I need to change? This here, yeah. What does it become now? 1,000. Yeah, very good. So this is now going to be only 707 newtons. So instead of getting this answer, you have this answer. There's also one other difference. Is the block moving or not moving? Moving. Which way is it moving?
Right.
It's moving to the right now. Because there's now a force going to the right of 1,000 cos 45. What's wrong, Fahad?
You have it's on the angle.
Yeah?
That should be this plus this is equal to this.
No? Not true. So here the vertical up equals the vertical down.
Yeah.
The horizontal right has no horizontal left. So what will happen to the block? It will start to move to the right.
Yeah.
If I don't want the block to move to the right, what do I need to add in? A force to the left. So let's add in a force. let's just call this force here friction. You know, friction like drag.
Yeah.
And if I don't want it to move, how much does this friction need to be?
707.
Not 7, no, oh yeah, it will be 707 because this is also 707. Friction will be 707 newtons.
Then it won't move.
Then it won't move. Yeah. Well, it could move, but at a constant speed. It won't accelerate, we should really say. Yeah. What's wrong with you? So look, just make some notes about what you should do if it's at an angle, but I hope you can see that if it's at an angle, that doesn't really make it any different, except that you have to now break it into two. That's all. Okay, let's have a look at some questions for you to try. Can I... What?
That's all.
Hang on, let me see. So... Yeah, okay. Yeah, okay, so here's your homework questions.
Did you upload it?
I will upload it after the class, but I want you to do them now for just 5 minutes. Yeah? So can you just do these for 5 minutes and then we'll go to the next topic? Yeah. Good. I like questions. Yep. Sure. Let me just stop the video here.